So we're moving into chapter 11, which is probability. And we're going to start in 11.1, which is empirical and theoretical probability. So now we're going to work in kind of more set in stone stuff. Statistics is great because it really is applicable to everything you have going on. Everything collects data of some sort. Your phone is collecting data constantly on what you browse and what kind of ads you enjoy and what you click on. Where probability is going to be more based off of situations you know the outcomes for. So if you think of any type of gambling, we're going to use that as a huge example because gambling is straight probabilities. You've got cards, those cards are not going to change. There's a set number of outcomes for it. And so your chance of getting, you know, a blackjack is one thing. If you have more information, so this card's out on the table, my chance of getting a blackjack is now going to be this instead. You really know everything that's happening in that situation, so we can come up with odds and determine what our chances are. So what we're going to start with in this section is really a lot of definitions to build and talk about some kind of simpler probabilities. So ultimately, an experiment is a controlled operation that yields a set of results. Okay. The possible results of an experiment are called the outcomes. Okay. An event for us is a subcollection of the outcomes of an experiment. Okay. And then when you look at the set of all outcomes, that's called our sample space. Okay. So we are predominantly going to be working with set situations. You're going to see marbles a lot. We're going to deal with the standard deck of cards. So if you don't remember a ton about cards, that's okay. We'll go back over all of the options within there. But to get accustomed to these words, let's take a look at some examples. The first one, we can talk about flipping a coin. So this is our experiment. What are your possible outcomes when you flip a coin?
Heads or tails?
Mm-hmm. So your sample space is exactly that. Your sample space is every single possible outcome. So it's usually labeled with an S. But you have two outcomes, the heads, which we'll just use an H, or tails for a T. You are flipping a coin once. So we have two different events that could occur. Usually we use E for the event. Your event could be you get a heads, or your event could be you get a tail. So it's a sub-collection or just a smaller portion of that sample space. Okay. Oh, nope. All right, what about rolling a die, a standard die?
The numbers 1 through 6.
You got it. So our sample space, which is S, is the numbers 1, 2, 3, 4, 5, and 6. Those are the only outcomes. One possible event would be the numbers 2, 4, or 6. Okay. What would this mean in words if this was your event?
Like you could only just get those numbers,
So what kind of numbers are those?
evens.
Even. So in words, this event would be an even number is rolled. So these would be the outcomes that would make us successful for that event. Okay.
Mhm.
Let's try one more. Flipping a coin twice. And let's figure out our sample space. Okay. What's one possibility when you flip a coin twice?
Double heads or double tails,
Double heads, double tails.
or heads and tails.
Yeah, so you get a heads on the first roll, tails on the second roll, or tails first, and then heads. But those are the only possibilities we have. And so if I pick a sub-collection of these, say my event is HHHT. I should be writing E equals for these, but not a huge deal. What's the connection between these two things in the event?
Heads is first.
Yeah. So in words, a heads is rolled first. Okay. All right. So the nice thing is with all of these, you're going to be able to figure out your exact scenarios for everything that you deal. But there are cases where you can't always do that, which is with realistic data, which is what we're going to have. So ultimately, there are two types of probability, just like there are two types of statistics. You've got empirical versus theoretical. Okay. And theoretical is exactly what it sounds like. It's theory. So this one's the more straightforward, I think. This is determined through a study of possible outcomes. Okay. While empirical is really going to be based off of trial and error. So maybe you flip a coin that's got weight to it. You don't know that there's an equal chance of heads and tails. So the empirical probability is relative frequency of an event. No, Macy. Someone walking in the halls. You were taking a nice nap. Go back to taking a nice little nap. Okay. So whatever you're dealing with, you're going to collect a bunch of information. There's going to be a percentage of people that like whatever it is you're going to work on. That's really just based off of your observances. So it's not based off of a worldwide survey. So this is really determined by observances. Of an experiment. Okay. And that's perfectly okay because that's what we have to work with. You can't test everyone.
It's like the most like common frequency that occurs. So you base your probability off of that. Okay.
Right. So what is it again you're working on for your project? I know I just read it this morning, but
oh my god, I don't even remember myself.
Okay.
The books and like the themes of books.
Right. So maybe you get
right.
100 people, you get that many responses, and you find that 30 of them like sci-fi. That's 30 out of 100. That's a 30% chance they like sci-fi. Is that realistic? Yeah. Maybe, but it could be that your data is also biased towards something because maybe you just had more people that like sci-fi that ended up doing your survey, which is okay. So theoretical is always the better, but most often we end up with empirical because we're working with what we've got. Their probabilities are really calculated in the same way. So the empirical probability of an event. E is found as follows. We use P to indicate probability. You put whatever event it is on the inside, so some type of description or words. It's going to just be a fraction. So it's the number of times event E occurred divided by the total number of times the experiment was performed. Okay. So 30 out of 100 people, that is your probability, 30% or 0.3. So this P is indicating probability. That's not how you spell probability, cannot spell. And then this is saying of event E. That's how you read that notation. Right. Because your total is going in the bottom, you're just going to have a portion out of the total. It's going to represent a percentage. You can never have a 150% chance something is going to occur. You can never have a negative chance something is going to occur. You get between 0 and 100%. That's it for probabilities. So based on that, the probability of an event should always be a number between 0 and 1. So i.e. 0% and 100%. If you get something different, you've made a mistake somewhere. Because I should not have a 150% chance that I'm going to roll a 7 on this die. Doesn't make sense. Okay. Feel okay so far?
Yes.
So let's try an example together. We'll just do a little bit more. We'll stop for the day. In a given week, a vet treated the following animals. We'll look at the animal, and then it tells us the number that was treated. For dogs, she saw 45 of them. She saw 40 cats, 15 birds, and 5 rabbits. Okay. We're going to determine 2 different probabilities. And this is empirical because this probabilities could change week to week. So determine the empirical probability the next animal she treats is a first dog. Okay. So what do we have to find?
The amount of time she treated animals in total.
You got it, yeah. So in total, the vet saw 45 plus 40 plus 15 plus 5, which if you add all of those, all of those together, you get 105. Oh, why is it moving so much today? Animals. So what would your probability of a dog be then?
45 over 105.
Got it. So since 45 of these were dogs, the probability a dog is seen next is, and I'm going to write it with this notation, use P to indicate probability. Our event is, it's a dog. It's the number of times dog was seen divided by the total number of animals seen. And you already said it is 45 out of 105. Okay. Depending on what my math lab tells you, if it says to simplify, unfortunately, you have to.
Mm-hmm.
But if it doesn't, then input this. So if you want
We
to,
don't have to. Oh, sorry,
go ahead.
we don't have to convert it into a percentage, or
No, you shouldn't have to typically. It usually will just want that number between 0 and 1. Sometimes it will have a percentage though. But if you do want to simplify this, if you have a calculator, it can do it for you. But if you have to do it kind of by hand, these are both divisible by 5 first. So if you divide top and bottom by 5, that will be 9. And then that will be 21 in the bottom. And you can keep going. They're both divisible by 3. So this is 3 over 7. And if you do plug this into a calculator, you'll see it's about 0.41 or 43. So about a 43% chance of it being a dog. What about a cat?
40 over 105.
The probability of a cat is 40 out of 105. And then to simplify, they again are both divisible by 5. So divide top and bottom by 5. That gives us 8 out of 21. And that cannot be simplified, but if it tells you to round, it's about 0.3.
Mm-hmm.
All right. So one of the nicest things that ends up coming out from these probabilities is something that's known as the law of large numbers. And this is where we kind of get those probabilities from. Basically, if I were to actually roll the die 10 times, I'm not going to get the same number, or I'm not going to get an even number for each value. It very well could be that I get a 5 on that die 4 of the rolls instead of an even number of times. So ultimately, this law of large numbers kind of tells you if I were to perform this experiment millions and millions and millions and millions and millions of times, that's when I'm going to see an equal number of everything going on. So these probabilities that you get really only apply when you're doing a lot of experiments going on. So my chance of getting a 5 is 1 in 6. But if I actually roll a die, I might not ever get it for a while. Okay? So what this ultimately states is probability statements apply in practice to a large number of trials. Okay. It's the relative frequency over the long run that is accurately predictable. Not individual events or precise totals. Okay. So basically, probability gives us an idea, but really you have to be performing these experiments over and over and over and over and over, pretty much forever to get those probabilities to actually occur. Because if I just have you die 100 times, you're probably going to get a 6 like maybe 10 times, but maybe you get a 5 like 30 times. That could happen. It would have to
Mhm.
be kind of like a million trials that you'll see the 1 and 6 for each. Do you have any questions so far?
No, I'm good.
So predominantly, we're going to be working with equal chances, though. We're going to assume everything is equal. So if each outcome of an experiment has the same chance of occurring, we say the outcomes are equally likely. Okay. And so all of these examples we've dealt with, rolling a die, flipping a coin, drawing a card from a deck, every option in there has the same chance of occurring. Okay. So when we're dealing with theoretical probability, we use the same notation. The theoretical probability of an event E is given by the following. You still use P of E, but now because we know all of the outcomes, it's the total number of possible outcomes in our denominator. And in the numerator, it's just the number of outcomes favorable to our event. Okay. So let's just try one example of this, and then we'll stop there for today, finish the rest of this on Thursday. Don't even know what day of the week it is. And let's start with a die. So a fair die is rolled. Let's determine the probability that first a 2 is rolled. What do you think here?
1 out of 6.
Yeah, you got it.
Okay.
For our sample space, we have 6 events. You can get 1, 2, 3, 4, 5, or 6. So if we look at the probability a 2 is rolled, in terms of our definition, it's the number of outcomes that result in a 2. Divided by the total number of possible outcomes, which is 6. So we have exactly that, a 1/6 chance of getting a 2. What about the probability an odd number is rolled?
3 over 6.
You got it. So our outcomes favorable to odd numbers the events that make us successful are we get a 1, 3, or 5. We roll a 2, 4, 6, that's not an odd number. So our probability of an odd number is 3 out of 6, or a 1/2 chance. What about the probability a 7 is rolled?
0.
0. There's no outcomes that give you a 7. So there are no outcomes resulting in a 7. So the probability we get a 7 is 0 out of 6, or a 0% chance of that happening. We're just going to try some more examples today and also see some possibilities or formulas that end up coming about. And we're going to work with a deck of cards. So we are told a card is selected from a standard deck of cards. We want to determine the probability that that the card selected is A5. Okay. And so if you aren't comfortable with a deck of cards, I'd recommend maybe bringing up like a picture of them. So if you just Google standard deck of cards, you'll see all of the options on there. But to kind of give you a rundown for a standard deck, I can now write standard today. I don't know why. Standard deck, there we go. In total, there's 52 cards, not including jokers or anything like that. You have 4 suits. So that's going to be your hearts, your diamonds, your clubs, and then your spades. Okay. And so there's 13 cards of each suit. So 13 hearts, 13 diamonds, 13 spades, 13 clubs. And then there's 4 of each card. So you've got the jack of hearts, jack of diamonds, jack of clubs, jack of spades. And then it starts at 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you have jack, queen, king, and ace. These are your different possibilities of cards. So in case you need this at any point, this gives you a nice overview of our deck. Okay. So if we want the probability of selecting a 5 just randomly out of the deck, there are 52 cards in the deck. There are 4 5s. Okay, so you've got the 5 of hearts, 5 of diamonds, 5 of clubs, 5 of spades. So the probability of getting a 5 is 4 out of 52. And you can simplify this a bit. So top and bottom are divisible by 4. And so that gives you 1 in the numerator, 13 in the denominator. So you have a 1 in 13 chance of pulling out a 5. If we kind of go off the reverse of this, the probability of the card selected is not a 5. It's kind of the opposite. So it's definitely not easy for me to sit here and try to figure out, okay, how many cards do I have in total then? Because any of these options is going to work for me. Instead, I know exactly how many 5s there are, so I just subtract them from my total number. So there are 52 cards in total. We're going to take away the 4 5s to leave us with 48 cards that are not 5s. So our probability of not getting a 5 is 48 out of 52. And again, both of these are divisible by 4. So if we divide top and bottom by 4, that's going to give us 12 out of 13. Okay. And really, if you kind of take a closer look at these, if I add those two together, that gives me 13 out of 13, or 1. So you have a 100% chance of drawing a 5 or not a 5. One of these two things has to happen. So this is going to be another formula we end up getting. So what we can say is that the sum of the probability that an event will occur And the probability that it will not occur is 1. Okay? So basically, the probability of event A happening plus the probability of not event A happening is always equal to 1. Okay? So you can rearrange this a bit, because depending on what you need to solve for, if you want the probability of not A, it's 1 minus the probability of A occurring, or vice versa. And really, you can see that from the prior example. Instead of sitting here and counting how many cards are successful for not getting a 5, we could just use this formula. So from the prior example, if we want the probability of not getting a 5, it's equal to 1 minus the probability of drawing a 5. So that's 1 minus 1 over 13. 1 is 13 over 13 minus 1 over 13. So you have a 12 and 13 chance of not getting 5. Okay. So this can be really helpful when you have something that's complicated to count. You might not want to sit here if I have like a million possible events and I have to see how many are successful. It might be easier to work with this formula and find the probability of the opposite event occurring. Okay. So let's try one last example in this section, and we're still going to work with more decks of cards. We are told one card is selected at random from a standard deck of cards. We want to determine the probability that the card selected is first the 5 of diamonds. Okay. So this is very specific because there is one card that is 5 and diamonds. So only one card is the 5 of diamonds. And diamonds are red, so I'm going to use red for that. So our probability of drawing the 5 of diamonds is going to be 1 out of 52. Okay. That is our only successful card. Everything else is not good. Okay. So let's try another one. Let's determine the possibility that the card selected is a red card or a black card. Okay. Well, as long as it's red or black, you're good. And in this case, every card is going to be red or black. So kind of going back up here to add some more info to your standard deck. Hearts and diamonds are red, where clubs and spades are black. So that's what color each of these is. So if on your draw, as long as you have a red or black card, you're good, you have a 100% chance of that happening. So here, every card is red or black. So ultimately, the probability of us drawing a red or black card is 52 out of 52, or 1. Your probability is 100% chance of this happening. If we change one word slightly, though, and say a red card and a black card, we have a single draw and we need that card to be both of these. That's physically impossible. So no card is both colors. So the probability of drawing a red and a black card in a single draw is 0 out of 52, or no chance it's going to happen. Okay. And then finally, let's figure out our chance that we draw a card greater than 3 and less than 7. We'll do less than or equal to 7. Okay. So I have to be greater than 3. I can't equal it, but I can go up to 7. So our possible cards are, we can get a 4, a 5, a 6, or a 7. And in reality, we have 4 of each cards. Okay. So in total, there are 4 possible cards and 4 events that give us success. So 4, 5, 6, or 7, and we have 4 of each of them. So in total, there are 16 cards that fit the outcome. So the probability that our card is greater than 3, but less than or equal to 7 is 16 out of 52. And again, both of these are going to be divisible by 4. So that gives us a 4 out of 13 chance.